This tutorial introduces PyTorch and covers the fundamentals needed for beginners to get started. First, let's use the fashion MNIST classification dataset with PyTorch. We'll import the necessary libraries, set a random seed for reproducibility, check the PyTorch version, and verify CUDA availability. This will help ensure consistent results. Then press the plus code icon to add another code snippet. Configure the device to use the CPU and print the result to verify that everything is set up correctly. Then press the plus code icon to add another code snippet. Define the data transforms with mean and standard deviation. Download and load the training and test datasets. Create data loaders, and print sample outputs from both the training and testing data. Then press the plus code icon to add another code snippet. Then, define the fashion MNIST category labels and print them to understand the different classes in the dataset. The numbers correspond to different types of fashion items, such as t-shirt, trouser, and pullover. Next, define a function to visualize sample images from the dataset to better understand the data. The output shows examples such as sandal, sneaker, coat, bag, ankle boot, and dress, each with its corresponding label number. Then press the plus code icon to add another code snippet. The next step is to build a neural network model, using a simple feed-forward architecture that includes the layers, a ReLU activation function, and dropout to help prevent overfitting. Model 2 is a convolutional neural network, CNN, for improved performance, which includes convolutional layers, pooling layers, batch normalization, dropout, and fully connected linear layers. Choose between Model 1 and Model 2 and print the selected model along with its parameters to inspect its structure. Finally, run the command to view the model structure and its parameters. Then press the plus code icon to add another code snippet. Then define the loss function and optimizer and print them to ensure they are configured correctly. The output will display the loss function, cross-entropy loss, and the optimizer atom including its parameter settings such as AMSGrid, betas, EPS, learning rate, and weight decay. Next, train the model over several epochs, where in each epoch the model processes the entire training dataset and updates its parameters. After training, evaluate the model on the test dataset to assess its accuracy and overall performance. Then press the plus code icon to add another code snippet. The training loop consists of starting the training process, training the model on the dataset, evaluating it on the test data, and updating the learning rate after each epoch. It also saves the best results and stores the metrics. Now, training begins and runs for 10 epochs, where each epoch represents a full pass through the entire training dataset. During each epoch, the model processes batches of data, performs forward propagation to generate predictions, calculates the loss using the defined loss function, and then applies backpropagation to update the model's parameters using the optimizer. At the end of each epoch, the model is evaluated on the test data set to measure how well it generalizes to unseen data. The system then outputs key performance metrics, including training loss, test loss, training accuracy, and test accuracy. These metrics help track the model's learning progress and identify whether it is improving, overfitting, or underfitting. In addition, the best accuracy achieved so far is monitored throughout the training process. If the model reaches a new highest test accuracy, it is considered the best performing version and its state is saved. This ensures that even if performance fluctuates in later epochs, the best model is preserved. Then press the plus code icon to add another code snippet. The next step is to visualize the model's performance by plotting the results. We create graphs for both training and test loss, as well as training and test accuracy across epochs. These plots help us analyze trends such as convergence, improvements in accuracy, and potential overfitting or underfitting. Then press the plus code icon to add another code snippet. Next, use sklearn to evaluate the model by generating predictions on the test dataset. Compute the confusion matrix to analyze how well the model classifies each category, and then plot it for visualization. Additionally, we generate a classification report that includes metrics such as precision, recall, and F1 score for each class. Then press the plus code icon to add another code snippet. The next step is to create a visualization that displays the model's predictions on sample images. Correct predictions are highlighted in green, while incorrect predictions are shown in red. This provides an intuitive way to assess the model's performance and understand its strengths and weaknesses. Then press the plus code icon to add another code snippet. Save the model along with the epoch, model state dictionary, optimizer state dictionary, training and test losses, and training and test accuracy, and print the results. Then press the plus code icon to add another code snippet. Load the saved model along with its parameters and use it to perform predictions on new, unseen data, demonstrating how to reuse a trained model in practice. Finally, use the trained model to make a prediction on a new, unseen image. The model predicts the class label for the single image, allowing us to test its real-world performance. This marks the completion of the tutorial. You have successfully completed the PyTorch for Beginners tutorial. You now understand how to build, train, evaluate, and use deep learning models for image classification tasks.